So, first of all, I would like to welcome you to the Kartini Research Reactor. So, here at the Kartini Research Reactor, this is one of the three research reactors that we have in Indonesia. So, in Indonesia, we have three research reactors. So, the oldest one is in Bandung, which we call Triga 2000, where Triga 2000 is a 2 megawatt design reactor, research reactor, Triga reactor. And then the second oldest is here in Yogyakarta, which is the smallest research reactor in Indonesia. And then the last one is in Serpong, in which we believe that this is the largest nuclear reactor in Southeast Asia. So the reactor at Serpong is 30 megawatt design and is operated at 15 megawatts. Okay, so the first of, I would like to introduce you to the research reactor here at the Kartini reactor. So the Kartini research reactor was built starting in the 1970s, and it finished construction in 1978, and it first achieved criticality in the 25th of January 1979, and it was inaugurated by the Indonesian president at the time, General Suharto, on the 1st of March 1979. So you can see the plaque of the inauguration on the picture on the right. So a small anecdote is that the reactor is named Kartini, where Kartini is a name of the heroine in the Indonesia, where she fought for women's rights and for education. And the Kartini research reactor is a light water pool type reactor. So it is quite different compared to the typical nuclear power plants. So she also has a design of 250 kilowatts and is operated at 100 kilowatts. And the reactor itself is a TRIGA design, where TRIGA itself is an acronym for Training, Research, Isotope Production by General Atomic. So the purposes of the reactor is already available in the name. So it's mainly used for training, research, and isotope production. But here in the Kartini reactor, we do not do isotope production because of the low power. Therefore, it has a low neutron flux. Hence, it is not feasible to be used to be used for isotope production. So, like a small joke that we use is that if we want to use the Cartesian reactor for isotope production, it would be very similar to trying to boil water in a kettle, but rather than using a stove, we are using a matchbox. So the heat is very, very small, and then the flux is very, very low. Therefore, every uh, isotope that we create, it will be quickly dissipate before the next one will be generated. The next one is I would like to talk a brief about several research reactors. So research reactors are quite different compared to nuclear power plants, where in nuclear power plants they use the heat to generate electricity, but here in research reactors we use neutrons, especially the neutron flux, for several things. So like I said, so like for isotope production and also for research. So there are several types of research reactors. So the famous ones are trigger reactors, like the ones that we have in Jakarta, Bandung, and also I believe the reactor in Malaysia, Puspati, is also a trigger type reactor. And then the second one is Argonaut, which is a French design. So it is an acronym for Argon Nuclear Assembly for University Training. So it is a research reactor, but is focused for training and some low power research. This is a French design. And the third one is a Slowpoke, where Slowpoke is not a Pokemon, but is a safe, low power critical experiment. This is very, very similar to trigger reactors, but the difference is in the fuel element and its design. So it has a lower critical mass compared to trigger reactors. And the last one is the material testing reactor, like the one we have in Serpong, the GRC-1TC reactor, and also another reactor that we have in France is a Jules Horowitz reactor. So it is a material testing reactor where it is designed to have a higher flux compared to regular reactors, where it is used for material testing. So it is used to intentionally damage stuff, so we know the limitations of the materials. Okay, next. This is a short view of an argonaut reactor. So argonaut reactor is typically low power, very low power, and they use a graphite reflector using an uranium aluminum plate fuel, where it is typically used for educational purposes. The nearest one closest to us, which is an argonaut reactor, was Moata, which is in Australia. It has 100 kilowatt, but it was decommissioned in 1995, and it is changed by Opal, the open pool Australian reactor. And then this is another reactor which is very similar to Triga, which is the Slowpoke reactor, where Slowpoke reactor is a tank-in pool reactor, where the Triga is a pool reactor, but Slowpoke is a tank-in pool reactor, where it is a pool that is enclosed inside of a tank. So they use a beryllium reflector, which is different with the Triga reactors, where the reflector is made from graphite, and the fuel rod, instead of uranium and aluminum, here we use uranium and zirconium hydride. The main point of the Slowpoke reactor is their low critical mass, so they can achieve criticality with a low amount of fuel. So one of the examples for this reactor is the reactor that they have at École Polytechnique de Montréal. This is a Slowpoke 2, and the schematic for the reactor is shown in this picture. So it is very, very similar to that we have in here, but they have a tank which includes the pool. And then the next type of research reactor that I would like to explain is about the trigger reactor. So the trigger reactor is a low power reactor, which is typically from 100 kilowatts to 3 megawatts. And it is an open pool design. And it can be used to be pushed up to 6,500 megawatts. Typical point for the trigger reactor, it is inherently safe. So the designers of the reactor from General Atomic, at the time they asked for Edward Teller and Freeman Dyson to design a reactor that is inherently safe and it can be operated by high school students. So not by high school graduates, but the high school students. So they can raise and lower the control rods without creating any hazards, and it will be completely safe. Another point of trigger reactor is it is operationally flexible and relatively inexpensive because they are robustly built, so they do not require fast maintenance and yeah, in the sort like this. It can also allow for a large variety of experiments. So experiments at trigger reactors, it can be done inside of the reactor core, inside of the reactor tank, and outside of the reactor tank itself. So there are lots of probabilities to do research at the trigger reactor. And the trigger reactor, they use low enriched uranium, where due to the nuclear non-proliferation treaty, so they changed the enrichment level of uranium, where before they can use up to 90%, but now they can use to maximum of 20%. And some trigger reactors are modified to MPR type reactors for a higher power output. So, for example, they have a 16 megawatt Triga reactor that is modified in Romania. They call it MPR16. Okay, now we will talk a little bit about the differences between Triga Mark 1, 2, and 3. So, I believe in Jogja, Bandung, and in Malaysia, they have the similar type. So, they are Mark 2. So, they are an above ground tank with several beam tubes. These beam tubes are used for the experiments outside of the reactor tank. So in the Mark 1, they have underground pool without any beam tube. So it will be very similar to the picture of the slowpoke. So here, the slowpoke, you can see that the reactor tank is built underground. But here in the Kartini reactor and then in Puspati and also in Bandung, they have a tank that is above the ground.
Oh.
I would like to show the configuration of the reactor or in so in particular we have six rings from ring A to ring F where in each ring they consist of different number of spots. So for example in ring A in reactor we have one spot here which we use as the window and then out, outside of the ring A we have the ring B where ring B there are six spots available and we fill them all with fuel except for one spot we use to fill with an instrumented fuel element so that it can be measured the temperature of the fuel near the center of the reactor core. And then at the ring C, we have two control rods, namely at T5 and T9, where we name those control rods as the safety rod and the compensation rod. I will explain a little bit more about the control rods later, because I believe in the afternoon we will have an experiment on the reactivity of control rods. So we will talk more about the control rods at that session. At ring G, we have 18 slots, and all of them are filled with fuel. At ring E, there are 24 slots, and 23 of them are filled with fuel, and one is filled with the control rod, which is the regulating rod. The outermost ring, which is ring F, there are 30 slots, and this not varied because at the ring F, we have the slot for the pneumatic transfer system. So at the transfer system, we can send samples from the pneumatic room to the reactor core within 3 seconds. So typically, this is used for neutron activation analysis, where we irradiate the samples for typically 3 to 5 minutes, and then we immediately count the number of radioactive elements inside of the sample. And then, besides the pneumatic transfer system, we also have a neutron source, which is made from americium and beryllium. So the neutron source from americium and beryllium uh, is a newer neutron source. Before we use plutonium and beryllium, where because as we know that plutonium is a fissile material, so if we use plutonium and beryllium, when the reactor starts and achieves criticality, we have to raise the neutron source because if not, the plutonium will be burned inside of the reactor core. The americium beryllium neutron source itself works by the americium emitting alpha particles, and then the alpha particles will interact with beryllium, and then they will create a neutron and diffuse. And we have also here another instrumented fuel element, where this instrumented fuel element is to measure the fuel temperature at the upper spring. And we also fill out several slots with graphite, where the graphite here is used as a reflector, where it will help maintain the neutron economy inside the reactor core. And this is a short overview of our reactor core and our grid. So this is the grid plate for where we put our fuel. So here we have 91 slots from ring A to ring F. So this is dependent on the power design of the reactor. So here in the company, which is designed for 220 kilowatts, it's very different compared to the one that they use in Puspati and in Bandung, which there are over 130 slots because they need more fuel to obtain a higher power level. And in this picture, this is the layout of our reactor. So the core itself is the one in orange, and outside of the reactor core, we have the Sun, where the Sun is used for long-term irradiation of samples. So for the Sun itself, we can irradiate up to 40 slots, where each slot can hold up to 2 samples. So we can irradiate up to 80 samples at the same time. And then the outer most part, and here is the blue one, is a reflector. So in this reflector, it's made from graphite. So as you know, graphite has a higher capacity for scattering. So the neutron leakage can be controlled. So every neutron that will escape the reactor core will be scattered and hopefully will return to the core. So we have a good neutron economy. And to the left and to the right, we have a thermal column and a thermalizing column, which is used for experiments using thermal neutrons. In the part, we have a stand for the reactor core. And for the one which number two, it is a fixed stand because of yeah, you know, in Indonesia, Malaysia, we often have earthquakes, so it is not more secure compared to using rails like they have in Illinois and in Pennsylvania, in the US, where they use mercury tractors, and to move the tractor core, they use like rails to move the tractor core. And if we use the similar system here, we are afraid that if there is an earthquake, the reactor core might fall off and will create some hazard and danger. Okay. The next one, I will talk about the leasing fan. So as I said, the leasing fan can hold up to 40 samples, and sorry, yeah, 40 slots, and each slot can hold up to 2 samples. So in total, we can have up to 80 samples at the same time. So it has a diameter of 31.75 centimeters, and it has a height of 27.4 centimeters. And for your information, so the fuel in the trigger, they only have a height of 75 centimeters, and they have an active height of fuel of only 38 centimeters. So it is quite different when you compare the fuel for trigger reactors with the fuel for nuclear power plants. So the fuel at the nuclear power plants, as we know, is made from uranium dioxide pellets, which are stacked into fuel assembly, which can be up to 4 meters. But here in trigger reactors, they are only one big slab of one big tube of uranium zirconium hydride, where inside they have zirconium, and then they are only about 75 centimeters high, and at the top and the bottom they have graphite also to increase the neutron economy. Okay, I apologize. So I hope this will be better. Is this better or the same? Okay, thank you. Also, if you have any questions regarding the explanations, just feel free to chat or just unmute and talk. So you can just ask any question and feel free to ask.
Okay, sure.
Okay. Next, I will try to explain a little bit about the pneumatic transfer system facilities. So here at the pneumatic transfer system facility, we have a multi-channel analyzer where we use a HPGE detector. So here we use an HPGE to measure the amount of radioactivity, and hence we can get the number of radioactive particles and then the concentration of the sample. And here these are the picture of the operators uh, using the pneumatic transfer system. So here this is how they operate it. The operator will insert the sample to the slot and then it will be sent. And here we use control panel to uh, we use the control panel to send and receive the samples to and from the reactor core. And this one is how the operator uses the MCA. And this is a top view of the reactor deck. So I hope you can see it clearly. So here, the one that I show you is the control rod motor mechanism. So inside of the control rod motor rod mechanism, there are some gears that will turn and adjust the control rod position according to the input from the reactor operator. This one, which is the same as this one, it is the housing to insert the sample to the lazy Susan. And this part, which is the same as this, is the apparatus that we use to change the slot for the lazy Susan. So this is done manually. To do so, we just raise this lever and then we turn the selector, and then this will put the sample at the correct slot. This is a short diagram of our cooling system at the Martini reactor. You receive any exposure when you are the deck. Okay, there is a question from Mr. Amir Gaddafi. So he asked about if we receive any radiation exposure when we are on the deck. So this question is a good question, and this will be answered when we do our practicum. So basically, when the reactor is off, there is no exposure at all at the deck. But when we are operating the reactor at a certain power level, there will be some radiation exposure. But at what level, we will show you during the practicum. But it is a good question. Okay, returning to our slide. So here I will show you a little bit about the cooling system. So in our system, we have two primary cooling pumps and three secondary cooling pumps with the cooling pumps are connected to three two cooling towers and also two heat exchangers. So in the heat exchangers, we have a shell and tube heat exchanger and also a plate heat exchanger. So I will show you the heat exchangers in the next few slides. And there is also another flow which is goes through the demineralizer system, where the demineralizer system is one of the important system because it relates to radiation protection and also on to the decommissioning part of this reactor. So as we know that when neutron interacts with materials, there are the possibility of the material becoming activated. Therefore, this demineralizer system is one of the important components to ensure radiation protection. Okay, on to the next slide. Uh, this is the cooling system inside of the reactor hall. So if you have been to a nuclear power plant or you have seen a schematic of a nuclear power plant, it is very different compared to the one that we have in the Cartinian reactor. So in the nuclear power plant, there are several buildings. So besides the reactor containment building, there is an auxiliary building, and then there's the steam generator building. But here in the Cartinian reactor, there's only one reactor hall, which houses the reactor itself and also its primary cooling system. So in the primary cooling system, uh, it is painted in yellow, and the secondary cooling system is painted in blue. So here we can see the primary cooling pump, so pump 1, pump 2, and then this is the demineralizer. And in the blue one, we have the plate heat exchanger and the shell and tube heat exchanger. So the shell and tube exchanger and the plate heat exchanger, they have the same capacity, which is for 250 kilowatts. But because of the advancements in technology, they have very different sizes. So as we can see, the heat exchanger is very, very big, the shell and tube one, but the plate is a lot more compact. So yeah, it is due to the advancement in technology, we can miniaturize the cooling from one that is this big to one that is this small. And this is the cooling system outside of the reactor hall. So these are the pumps for the secondary system. We have 3 pumps. And then these are the cooling tower for our reactor, which is quite small. So don't compare them to the ones at the nuclear power plants, because yeah, this is only rated for 250 kilowatts, which is like what, one eight, 1/600 of nuclear power plant maybe. So yeah, it's very very small. And to operate the cooling system, we have to fill in the forms. So it is something like this. This is taken from November 2019. So to operate the primary cooling system, we have to check the pumps and also the pipes and valving. So for the pumps, you have to check whether it sounds right, and then the motor temperature is it too hot or not, and then we have to check how it works, and then also check are there any leakages on the pump. On the piping and valving, we have to check on the any leakage of water and also and how do they work. And typically during each operation, we note on what is the date of the day, and then when it starts, when it ends, and then the number of the pump used, and then who is the operator for the day. The similar is form is filled when we operate the secondary system, where when we operate the secondary cooling system, we have to check for the cooling tower and also for the pump. So for the cooling tower, there are some specifics. You have to check the water availability, and then the water supply, and then the water flow, and also uh, are there any sufficient excess water that overflows from the cooling tower. So there is a small anecdote, is that when it is the dry season here in Yogyakarta, there is not enough water so that we are not able to do operations without using water from outside of the facility. And this is the demineralization system, where they have filters inside of this one, and then after it is filtered by the filter, they are put into a resin that is housed in this tank. So the resin that we use in this tank is called Amberlight 150, which is a mixed cation and anion resin. So the any impurities that are available inside of the reactor water will be filtered, and then it will be held by the resin inside of this demineralizer system. So having this demineralization system, we can protect from the hazard of any excess radioactivity in the water or any ions that can interact with the tank materials and that can corrode with the tank itself. And this is the view of the control room at the past. So this was taken around 6 to 7 years ago. So they have several monitors and then the scheme for the reactor and its cooling. So here, this is the process computer where it shows the position of the control rod and then the power output of the reactor. And then this is the CCTV that shows the condition around the reactor building and inside of the hall. And these two are used for auxiliary system. Uh, Before we go to the instrumentation system, do you have any questions? If not, we will continue with the instrumentation system. So here, uh, as a means of nuclear safety, uh, besides redundancy, we also have diversitor system. So I'm sure that all of you know about redundancy, where they have the same system in multiples. So to ensure that if one system fails, there is another to back up the system. But here in Diversitor, we use two systems that operate slightly differently to have the same measurement in two methods. So for example, here we measure using the system by two detectors. One here is a compensated ionization chamber, and the other is a sorry, uh, fission chamber and a compensated ionization chamber, where they both give different outputs. So the compensated ionization chamber, they output in current, and the fission chamber, they output in pulse. So they have a different system. The CIC will be connected to the linear channel, which indicates the power from 0 kilowatts to 100 kilowatts. But here in the fission chamber, they output the power in logarithmic. So starting from 10 minus 6 to 100 kilowatts. And these systems are connected in the end to the radiation protection system, reactor protection system, where the reactor protection system will automatically trigger scram when certain conditions are met. So typically the conditions to trigger scram in our reactor is when the period it reaches 7 and the power is at 110 kilowatts. Well, this is maybe, if you can say, it is a little bit overkill because our reactor is designed for 250 kilowatts, but we are taking this value conservatively, and the limits for our reactor to trigger scram is at 110 kilowatts. So these are the instrumentation system of our reactor. So this is the high voltage power supply, which supplies power for our instrumentation system. So our instrumentation system mainly focuses on these two, the NLW2, which outputs the power in logarithmic, and also the reactor period. The reactor period is the indication on how much time is needed for the reactor to increase the power in E times. So E is the 2.71. So yeah, uh, if the smaller it gets, it indicates the rise in power is too quick. So when this system triggers that the period is below 7, it will automatically trigger the reactor to do scram. And finally, this is the NP1000, which indicates the power linearly from 0 to 100 kilowatts. This is the control system. So here the detectors, they are connected to the NLW2 and the NP1000, and then there is connected to the analog to digital converter, and then it is connected to our regulating system, our slave computer, and parallelly the operational keyboard is connected to a switch module and a relay, and which both are connected to our control rod mechanism. This is our operational keyboard. So it is very, very simple. So this is the system that we use to raise and lower our control rod. So there are three control rods: the safety rod, the compensation rod, the regulating rod. The red one is to raise the control rods, and then the green one is to lower the control rods. There is a safety button that we have to press, one in yellow. So when raising, this is the operational keyboard. So this is used to raise and lower the control rods, one for each control rod. So this is for the safety, compensation, and regulating. And to raise and lower, we have to press the button and also the safety button. So this is to ensure that we raise and lower the control rods deliberately, so that there is no accidental movement of the control rod. And on the top, these three buttons are used to trigger manual scram of the reactor. So when the operator senses that the reactor is not operating safely, but the scram is not triggered automatically by the system, the operator can immediately trigger scram by pressing these three buttons using this flag. This system on the left is a system that we developed from from the image on the right, it is showing the manual system, and on the left, it is showing about the automatic system, where the automatic system will raise and lower the control rods automatically according to the request of the operator, where this is can be done on low power reactor, where in nuclear power plants this is quite difficult to be done because the conflicting inputs of when we raise and lower the control rods in rapid succession. So when we raise and lower the control rods in rapid succession, uh, the conflicting inputs will create some confusion in the computer. Okay, for the next slide. We will show about the ventilation system in our reactor. Where in the ventilation system in our reactor, on the left picture, we have a blower which sucks the air inside of the reactor hall and then exhausts the sucked air from the reactor hall through our chimney, which is on the picture on the right. So in the picture on the left, the ventilation blower system, it can suck and replace the air from inside of the reactor hall 6 times each hours. So we are sure that the air that we breathe inside of the reactor hall, we are sure that it is free from any radioactive particles and any radioactive gases that may form inside of the reactor hall. The next picture will show about the next picture will show about the checklist that we have to fill when we are operating the reactor blower. So here we have to fill the date and time when we have to start, and then when we finish the operation, and then we fill out the changes, the differences in air pressure when from the inlet and the outlet,
and then we check the blower. So whether the blower works properly, and then whether the motor works properly, and then the V-belt for the blower, whether it is in line or not. And then we have to check the number of blower that we use. So here in the Cartini reactor, we have 2 blower units, which are used interchangeably. So blower number 1 is used in odd numbered months, so like in January, March, May, and so on. And then the blower number 2 is used in the even numbered month, so like in February, April, June, and so on. This is a short view of the typical technical specification of the Cartini reactor. So here, the specification of the Cartini reactor, the maximum power is at 100 kilowatts, and then the minimum period is at 7 seconds. The maximum power that is allowed by the system is at 110%, which is at 110 kilowatts. And then the tank surface temperature is maximum at 40 degrees Celsius. And then the maximum fuel temperature is at 530 degrees Celsius, which is far from the limits of the fuel, where the fuel theoretically will melt at over 1,100 degrees Celsius. And then when we operate, it is only at maximum of 180 degrees Celsius. The primary and secondary flow is shown on the screen. So here we have a primary flow that is lower than the secondary flow, because we have the same diameter of tubing. Therefore, the pressure in the primary cooling system is lower than the secondary cooling system, where the lower the pressure in the primary cooling system means that if there is a leakage in the heat exchanger, where there is contact between the primary cooling system and the secondary cooling system, it means that the water from the secondary system will enter the primary system rather than the primary system going to the secondary system. Because when there is a leak and then there is a water that is coming from the primary cooling system to the secondary cooling system, there may be some radioactive particles will be lost into the environment, because due to the transfer from the fuel to the primary cooling system to the secondary cooling system and out through the cooling tower. And then we monitor the concentration of silica, magnesium, calcium, and natrium inside of the water, because we know that the magnesium, calcium, and sodium, they are ionic elements, where the ions that they may interact with the aluminum tank inside of the reactor, and then they may cause some trouble, as they may increase the rate of corrosion in our tank. And finally, here is on the conductivity of the water reactor tank, where the conductivity is between 0.2 ohms to 0.5, and then the inlet and outlet, they indicate how is the purity of the water inside of the reactor system. And in the below part, it indicates the radiation exposure, the limits of radiation exposure at several locations. So like in the upper tank, and then at the control room, the reactor deck, the demineralizer, and then the thermal column, the subcritical, and at the bulk shielding. So the question that you asked previously is slightly spoiled by this part, because we know that the deck, there is a slight radiation exposure. So the next part, I will show you about the startup procedure. So for the startup procedure, we have to fill in this form. So yeah, you can read this. This is in Indonesian, so maybe you can slightly understand slightly, but this is in English, this one. Oh, sorry, wrong button. This is the startup checklist, which we have to fill. So we have to fill about the number. So the number is depending on what is the previous number, and then the date, and then about the primary cooling system, and then the secondary cooling system, the blower, and then the reactor itself, and then the instrumentation system of the reactor. This is the one in English, so I hope you can fill out this form. So when we do today's experiment, you can fill out this form together. So here in this practical, we will fill out the checklist like this, and together, and then we will do some power maneuver several times, and then in the end we will do some discussions on the results of today's practicum. And then this is the checklist we will fill when we achieve a certain power level. So for example, for today, we will go from 0 to 100. When we are at 0, we fill out this form. And then when we are at 100, we fill out this form. So like in the power checklist, we will do a checklist on the temperature, but instead of on about the blower, we have to fill in the fuel temperature, and then the radiation exposure will be filled so that we are sure that there is proper radiation shielding for the operator, so that there is no excess radiation that is received by the operators. And then when we shut down, we have to fill out this form, which is very, very similar to the previous forms. Okay, this is the references that we use for today. So from John Lamarche, and then Suprawardhana, Salam, and then